so let's get started. I'll come and collect all those in just a moment. I'll give people a few more minutes to trickle in. What I want to start talking about today, in the next couple of days, are logarithms, logarithmic functions. And see, as I've done it 2 times in this class, when I say the word logarithm, how many people have an idea what I mean? Many people would already describe themselves as pretty comfortable with logarithms. Oh, okay. Cool. So let's start with even what are the logarithmic functions? What do they mean? And as indicated by the title of this document, they're just inverses to the exponentials. So that's enough to sketch graphs, right? For instance, what does the graph of 2 to the x look like? Right, it has this vertical asymptote as x goes to, nope, it has a horizontal asymptote as x goes to negative infinity, 2 to the x goes to 0. Where's the y-intercept of 2 to the x? What's 2 to the 0? 1. So the y-intercept will be at 0, 1. And then it'll just keep on growing. It'll grow quickly, but not quickly enough to have any vertical asymptotes. So let's try to graph the inverse function. If you know what the graph of a function looks like, how do you get the graph of the inverse function?
Just flip the x and y points or coordinates.
Yeah, flip the x, y coordinates. So let's do that. So 2 to the x goes through the point 0, 1. So what point should the inverse function to 2 to the x go through? 1, 0. I see points down here where x is negative a big number and y is pretty close to 0. Right, when you plug in a really big negative number for x, 2 to a negative really big number is close to 0. So what point do we see on the inverse function? Well, we should see a point where the x coordinate is really close to 0, but positive, and y coordinate is a very negative, very big number. Nice. So there's the graph of the inverse function to 2 to the x, which is just denoted as the log base 2 of x. People feel okay? So let's try to see what analysis we can get done just by thinking about these inverse functions. So I guess the first thing to know is just think about what inverse functions mean. When someone says y equals f inverse of x, that means if you plug y into the function you started with, you better get this back. Inverse functions are supposed to undo the original function. So the same is true for logarithms. If someone says y is the same as the log base b of x, that's the same as saying b to the y is equal to x. So those two equations mean the same thing. I'll say that this one is in log form, and this is an exponential form. So, for instance, if someone says 4 is equal to the log base 3 of 81, what they're really saying is that 3 to the 4th is equal to 81. Is 3 to the 4th equal to 81? It is, right? So that means, yeah, 4 is the log base 3 of 81. So you know how to evaluate some logs as long as you know what corresponding exponential fashion. When someone says negative 1 is the same as the log base 7 of 1 over 7, what they're saying is 7 to the power negative 1 is equal to 1/7. And is it? Yeah. And going back and forth between those two different ways of writing logarithmic equations can often be useful. Let's even just see some quick examples. So here's an equation that's in exponential form. it's pi cubed is equal to m. You know what? I think I want some persistence on the board. So let's try to translate between. So pi cubed is equal to m. There's something in exponential form. And let's see if we just try to match up the symbols. What's the base of the exponent you see in that thing? I see pi to the third power. So that pi has the job of b. So that means I should be able to rewrite this in log form by saying the log base b of the thing that's on its own of m is equal to 3. That makes sense? Let's do the rest. E to the x is equal to 9. So what's the base of that exponent?
E.
E. So there's the b that I need to use. So this should mean that the log base e of 9 is equal to x. And I want to introduce a piece of notation. Yeah.
Yeah, and I think you're going to address it natural log.
Yeah. So e, this number that's around 2.7 and some change, has really nice properties from the point of view of calculus, which is why mathematicians regard e as the natural number to put in the base of an exponent or on the base of a log. As a consequence, it's standard to refer to log base e of x as ln of x. So that's just the ln of 9. So ln is log base e. Maybe I'll even jump up here to comment that I should have made earlier. Let's just think about notation, conventional notations.
Move down a little.
Oh, yeah. So when someone just says log of x without specifying a base, you kind of just need to be psychic and know what they mean. Or have found like the sentence written somewhere where they tell you what they mean when they don't write a base. In the book, they'll use log of x when they mean log base 10. But don't trust that whatever computing device you're using uses that same convention. It might. For instance, at Wolfram Alpha, when you just write log of x, it'll assume that you mean log base e, the natural logarithm. Mathematica, I think, assumes log base 10, but I'm not positive. So whatever computing device you use, you need to be able to figure out how to specify a base, and if you don't specify a base, you need to know what it means. X to the fourth is equal to 81. How would you rewrite that in log form? Yeah.
The log base x of 81 equals 4.
Log base x of 81 equals 4. And let's just think from the point of view of like solving equations, if we've made our lives better or worse in each of those moves. If you wanted to like solve that equation for m, is that better in exponential form or log form? Exponential. It was already solved. Ooh, that's a loud ringtone. E to the x is equal to 9. Did we make it better or worse by writing it in log form? Better, right? We now have x is equal to a thing. We have solved. We worked into something which maybe you don't know how to compute, but we can resort to a machine. X to the fourth is equal to 81. Did we make our lives better or worse? Well, we certainly didn't like just solve it by doing that on its own. It wasn't solved beforehand, but in fact it's easy to solve. What would you want to do to solve that equation for x? Take the fourth root, yeah. And I guess that's even like 3. Nice. Let's go the other way. Let's write logarithmic equations in exponential form. Log base pi of 3 is equal to m. You can rewrite that as 3 is equal to pi to the power m. ln of x is equal to 9. Well, remember that's the log base e of x is equal to 9. So what do you get when you rewrite that in exponential form?
e to the 9 equals x. Log base x of 4 is equal to 81. What do you get when you rewrite that?
X to the 81 equals 4.
Nice. And again, we see, well, this equation was already solved, so we made our lives worse by rewriting. This one, hey, doing just that manipulation solved for x. That's nice. Log base x of 4 is equal to 81 became x to the 81 is equal to 4. It's still not solved, but can you just write down the solution to that equation now? I guess you need to take like the 89th root of 4. But, I mean, that just is what it is. Nice. Any questions so far? Cool. So a lot of the computations that we'll do for logarithmic functions we'll just have to resort to a computer if we want to get decimal approximations. We can say some things about how big a log needs to be. If we want to do anything precise without tools that come from calculus, we just have to resort to using a machine. So let's do that. Oh, in fact, how many people have ever seen any of these old engineering logarithm tables? Before the age of modern convenient computing, engineers who just needed to make reference to logs and exponentials just had big old books which would tell them that the log of 4 is something to however many decimal places. They would just need to look it up in a book. That's not related to what we're doing right now. Let's make some computations without looking them up in a book. Let's just do it by thinking about them. Let's compute the log base 4 of 42. And here's how we'll do it. I don't know what the log base 4 of 42 is, but I can certainly give it a name. Let's call it, I don't know, what's a good variable name? Sure. Log base 4 of 32 is equal to x. I would like to know what x is equal to. What do you get when you rewrite that in exponential form? 4 to the power of x is equal to 32. Wait, does that bring up memories of like what happened about a week ago today? Is there a common base between 4 and 32 that you could take advantage of? What common base are you thinking of? 2, I think. So we could rewrite that as 2 squared. Ooh. If you do need to go because it's an important call, you can go and take the call.
No, I apologize.
Okay. What's 42 as a power of 2? 2 to the 5th, I think. So we can eventually rewrite that as 2 to the 2 times x is equal to 2 to the 5th. So 2x is equal to 5. So what is x?
5 halves.
X is 5 halves. So the log base 4 of 32 is equal to 5 halves. I assert that we can do something similar for the log base 5 of 625. And let's try to do it. So I don't know what it is on the nose, so I'll just give it a name. I'll call this, I don't know, x already was used in the previous one, so I'll call it y for now. I'll rewrite that in exponential form, giving me 625 is equal to 5 to the power y. And assuming that the previous technique works, that must mean that 5 and 625 have like a common base. What do you think that common base must be? 5. It's like the only option by looking at the right-hand side. And let's try to write 625 as a power of 5 by just writing out some powers of 5. What's 5 to the 1? 5 to the 2? 25. Multiplied by 5 again to get 5 to the 3 is 125. Multiplied by 5 again to get 625. Hey, cool. So 625 is 5 to the 4. So 5 to the 4 is 5 to the y. So what is y? Nice. So the log base 5 of 625 is 4. So you can make some computations on the nose by just rewriting in logarithmic form and figuring out that, rewriting in exponential form and figuring out that you already know the solution to that exponential equation. But obviously you can't always do that. Remember last time we wrote down the equation 5 to the x is equal to 7 and said, well, we just kind of can't write down a solution to that using the technique we know? Well, now we kind of can. Let's solve 5 to the x is equal to 7, and we can even get a decimal approximation. So there's an equation that's in exponential form right now. And it's not something that I just know the solution to. There's not a common base to use. What do you get when you rewrite that in logarithmic form?
Log base 5 of 7.
You get log base 5 of 7, Gesundheit, is equal to x. Hey, did we just successfully solve for x? Cool. If you cared about the bigness of that number, I mean, I guess by looking at it, I know that if you're going to raise 5 to a power and get 7, you need to raise it to at least the first power, but you can't raise it to the second power. That would be too big. So whatever this is, it'll be 1 point something. Let's use a machine and figure out what that something is. So, how many people like using their handheld calculators? So what I suggest doing is consulting a manual and figuring out how your calculator will want you to input logs of various bases. I probably can't help you with that without going online, looking up your calculator's manual, and reading the manual, but you can do that yourself just as easily. I'll use this. Let's compute the log base 5 of 7. Log base 5 of 7, good. There's something that we'll figure out later. If you know how to walk in any given base, you can walk in any base by dividing. We'll explain that on Friday, I think. And there's the decimal approximation, somewhere around 1.2. People feel pretty okay? Let's solve some more equations. So let's do things that are more involved. Let's solve the equation 3 to the x to the power 2 is equal to 8. And there are two different, there are two different strategies for solving this. Maybe I'll give you guys a choice. I can keep talking and you can tell me strategies to use. Or I can just pause for a bit and let you guys solve it on your own. Kind of people just like me to keep talking. Okay. Then I will, but maybe I'll get suggestions from you guys first. What would you want to do to that equation? What's a move you would want to make? Yeah, I see there's a square going on the outside. So let's undo that square by square rooting. So there are two different strategies, so I'll strat 1. That'll give me 3 to the x is equal to the square root of 8. And maybe I'll even put a plus or minus there. And maybe I'll figure out if that plus or minus needs to be there. What's the range of 3 to the x? Is 3 to the x ever negative? So is it possible for 3 to the x to be equal to negative the square root of 8? So we just need, the only possibility is the positive branch. The range of exponential functions contain only positive numbers. So now I have 3 to the x is equal to 8. Is that an equation that's just in exponential form now? And the only thing we don't know is the thing in the exponent. So let's rewrite that in log form. What's the base in that exponent?
3.
3. So that means I can rewrite this in terms of log basically, Gesundheit. To get x is equal to the log base 3 of the square root of 8. Did we just succeed in solving this equation? I think so. And what is the log base 3 of the square root of 8 approximately equal to? Let us consult the oracle. Let's compute the log base 3 of the square root of 8. All right, so there's like a simplified version, but all I want is a decimal approximation right now. This is somewhere around 0.95. Cool. How many people solved it a different way and got a different looking answer? Okay, I mean, I guess I didn't really give you time to. Maybe I'll suggest here's another starting move. Before trying to just undo everything on the right-hand side, we could simplify the right-hand side, right? What is 3 to the x to the power 2 the same as? It's the same as 9 to the x, so maybe 3 to the 2x, but 9 to the x works. So here's a second strategy. Let's rewrite 3 to the x squared as 9 to the x is equal to 8. Hey, neat. Is that equation now just like easy to solve? What's the solution to that equation? Yeah. The log base 9 of 8. Yeah.
And when it's in parentheses, we don't square the exponent then, or do we?
Ah, okay, so like this is a different problem, right? Yeah, so there's no rule for like 3 to the x squared simplifies. I guess you could write that as 3 to the x, but that makes it worse because more x's have suddenly shown up. So instead, let's
Question.
yeah.
With the problem that you just showed, both answers in log form would be sufficient?
What I'll talk about as of next time is some things you can do to simplify, some algebra for logarithms that will allow you to simplify. I'm happy with either of those. Those are both exact answers. If anything, log base 9 of 8 looks simple, right? That seems preferable to me. Though, by looking at this, there's no way to see that that should be simplified right now. Maybe we should double check that these answers are both consistent by having a computer tell us what the log base 9 of 8 is. Let's compute the log base 9 of 8. Is that pretty close to the same as what we got the first time? Cool. Then I think I believe both of these answers. So I guess another thing to note is, let's suppose that you and your friend are walking together. I assume that you would walk with your friends and not your enemies. If you get answers that look different, that might mean that one of you has done the problem wrong, but not necessarily. You might just have different looking answers that are really the same. Computer decimal approximation using the machine. If you both have the same answer, decimal approximation wise, then probably you did it right. Nice. So let's, in the interest of keeping pace, let's move on to like an application-y problem. And this was not yesterday, this was last week. We talked about the trouble with triples, right? The trouble with triples is that a population of triples doubles every hour. So if you start with one triplet times 0, then the number of triples you will have after t hours is given by 2 to the power t. Well, here's the situation. There's a population of triples aboard the Starship Enterprise. And by a quick modeling problem, they found that the ship's life support will be overwhelmed once the population of triples exceeds 30,000. How long does the crew have to solve the problem? How long will it take before the population hits 30,000? So what equation is this asking you to solve?
30,000 to the t.
30,000 is equal to 2 to the t, because that's the population. So this is just asking you to solve 30,000 is equal to, well, I'll write P of t because that's the name of the population, is 2 to the t. Does that look like an equation that you can solve? What do you get if you rewrite that in, say, logarithmic form?
Log base 2 over 1,000 equals t.
And maybe before we do like a computation, let's just try to make a preliminary guess about how big you think that number will be, just in terms of how many digits do you think it will have? I don't know, starting with like a 5-digit number. So what do you think? After we take the log, how many digits? Well, what do you think? How many digits do you think we'll have? 1? More than a 1-digit number. How many people think we'll end up with a 2-digit number? 1? A few. How many people think we'll end up with a 3-digit number? 4-digit number? I assume that the rest of you think it'll be 5 or more digits. Let's find out. Let's try to compute the log base 2 of 30,000. That's the number of zeros? And I know what I already said what the decimal approximation is. So t is approximately 15 hours. Maybe it's important to note that if time gets to 15 hours, then you've already lost because it happens at 14.87 hours. So that's kind of surprising, right? If we have a quantity that's doubling every hour, it still only takes like 15 iterations to exceed 30,000. So one thing that maybe you're noticing here is, right, exponentials grow really, really fast. So the inverse logarithm should actually grow pretty slowly, which is what we're seeing here. Nice. How do people feel? Examples seem okay? So you can do some algebra with logs by just remembering that logs are inverses of exponentials. Let's try some trick questions. Let's try to evaluate the log base 2 of -3. And I know that we could resort to just using a machine, but let's try to think of it this way. Let's try to think of it the same way as we did for the things on page 1. So let's give that a name. Let's call that, I don't know, I used x and y already, so I'll call this one z. So if I want to solve if I want to evaluate log base 2 of -3, well, I could rewrite that in exponential form and see that I want to determine a number, z, for which 2 to the z is equal to -3. Is there any power of 2 which gives you -3? Why not? Powers of 2 are always positive? Oops. So 2 to the z is always positive. No such number exists. So maybe that tells you something. That tells you that you couldn't have possibly plugged -3 into the log base 2. -3 isn't in the domain of log base 2. You can't make sense of the output. You can't make sense of what that thing will be. Do you think there's anything special about that -3? Could that have been -7 and I would have said the same words? So it looks like we can't plug any negatives into logs. So the domain of log doesn't contain any negatives. So let's think about this. So the domain of the logarithm function, in general, how does the domain of an inverse function compare with the original function? Yeah, it's flipped. It'll be the range of the inverse function. So the domain of log base b of x is the same as the range of b to the x. And what's the range of b to the x? 0 to infinity. Infinity is never included. Is 0 included in the range of b to the x? No. So the range of any logarithmic function is always 0 to infinity, excluding 0. Nope. The domain of any logarithmic function is 0 to infinity. I'm going to rewrite that because I misspoke at least once. Domain of log base b of x is 0 to infinity.
Nice. Let's try another trick question. Let's try to evaluate the log base 1 of 4. So we'll try the same thing.
Let's give that a name. Let's call that w. So if I want to know what the log base 1 of 4 is, I can rewrite that in exponential form to see that 1 to the w should be equal to 4.
So what power is big enough that I can raise 1 to that power and get 4? Well, you can't, right? 1 to the w is always 1. So what's the payoff there? Log base 1 doesn't make sense.
The logarithmic function log base b of x only makes sense when b is positive and not equal to 1.
Cool. Let's
Do some graphical things with log 6.
So let's start by just remembering what the graph of b to the x looks like. Well, what does the graph of b to the x look like for any b?
Goes through 0, 1. And then it'll do something like this, right?
At least it will some of the time. The graph of b to the x will look like that as long as b is bigger than 1.
When b is between 0 and 1.
That's what the graph of b to the x will look like. What does the graph of 1 to the x look like? 1 to the x is always 1. So it'll be like a flat line at y equals 1.
Maybe I'll put it dashed because this is like the case I don't care about. So there's 1 to the x.
So let's even just look at these. Is 1 to the x even a one-to-one function? No. So of course I can't talk about log base 1 of x. I'm trying to invent something that's not one-to-one. Otherwise, if I want to sketch the graph of logarithmic functions, I'll just take those and flip them over the line y equals x. Switch the job of x and y.
So everything goes through the point 0, 1. So all of the logarithmic functions will go through the point 1, comma 0. The green function, in the case that b is bigger than 1, well, I see these y values getting close to 0 as x goes to negative infinity. So conversely, the inverse function, as the x values get close to 0, the y values will go to negative infinity. Oh, yeah. So there's the graph of log base b of x when b is bigger than 1.
If I want to graph the log base b of x when b is between 0 and 1,
Well, actually, let's look at this. So to go from that green graph to the blue graph,
what inversion has happened? It looks like I've just reflected over an axis. The y-axis, I guess. But like inverse functions switch the job of x and y.
so instead to get log base b of x when b is between 0 and 1, I'll just take this graph and flip it over the x-axis. So there's the graph of the log base b of x when 0 is less than b is less than 1.
Nice.
And now let's even just double check some things that you already know by looking at these graphs. By looking at those, tell me, what is the domain of either of those? What's the domain of a logarithmic function? 0 to infinity. So that's also on the previous page, but it's nice to confirm you by looking at a graph. Right, because that's like, what x values do you see on there? And notice it never actually makes it to x equals 0, so 0 is not in the domain. 0 is excluded. What's the range of those functions? All real numbers. Log base b of x has an x-intercept. Where is its x-intercept? The logarithmic functions have vertical asymptotes. What vertical asymptote do they have? And again, it's like a different looking vertical asymptote than like our rational function has.
Should be x.
Yep, because it's vertical. Thank you. So the next thing that I think I want to do is, we know qualitatively how all of these graphs will look, right? They'll all look like the green graph right there. But presumably they're not all exactly the same function. There will be some sort of quantitative differences between them. So let's sketch a graph of a lot of those and see how they compare. So let's plot log base 2 of x, log base e of x, even though that's the same as ln. Wolfram Alpha will be fine to write log base e. Log base 5 of x, and log base 10 of x. Oh, and ignore the stuff to the left of the y-axis. It's doing something silly.
Change over so you're projecting the computer.
Oh, thank you. How long were you guys going to let me get away with that? I guess until then. Let's plot all of these from x equals 0 to x equals 10. So they're there. Log base 2. See, log base 5, log base 10, log base e, log base 2. How does it look like those graphs compare?
They all have the same x-intercept.
All the same x-intercept?
But the larger the base, the horizontally steeper they are.
Yeah, so the as the base goes up, they're getting like squished down.
Yeah.
So the larger the base, yes, I won't even bother drawing them. As the base grows, looks like log base b of x gets, well, I'll even use the graphical one, compressed vertically.
You'll have to switch your monitors.
This is the danger of days when I want to use like lots of computer stuff. There are other ones that have like 2 projectors, so I can have both things going. But those rooms are terrible for different reasons. This room is terrible for its own little reasons that I've gotten used to. Nice. So you now know what the graphs of the logarithmic functions all look like, and you even know kind of qualitatively how they compare. In fact, maybe that suggests that if you want to get log base 2 of x, you should just take log base 10 of x and like multiply it by something. I wonder what that something is. We'll figure that out next time. So let's do just a few more things. Let's just think about, oh, there's even a sales pitch. That's a sales pitch for something called the change of base formula, which you can either look ahead in the book to see what it says, or you can wait till Friday when it'll be stated in the notes. So let's do some things just by remembering how to deal with functions. Let's find the domains and x-intercepts of some functions.
Cool. So how do you find x-intercepts of a function? Set y equal to 0. So you set the whole function equal to 0.
Let's find the x-intercept of this Fox function. So that means I want to set log base 2 of 3x minus 4 equals 0.
And I want to know what x is. So what would you want to do to that equation to figure out what x is?
Rearrange that exponential form.
Yeah. Put it in 2 to a power instead. So it looks like that base is going to be 2.
So I'll get 3x minus 4 is equal to 2 to the power 0. Ooh, I know what 2 to the power 0 is. What's 2 to the 0?
1.
Does that now look easy to solve for x? What do you need to do to solve that for x? Add 4 both sides, divide by 3. So what's x?
Cool. Let's find the domain. So let's see, 3x minus 4. If you ignore the logarithm and just look at 3x minus 4, does that have any problems in its domain? You can always do 3x minus 4. What things are you allowed to plug into logarithms? Can't plug 0 into a log. So anything positive. So that's different from square roots, right? Because you can take the square root of 0. You can't take the log of 0.
So if you want to compute the domain, well, what you need to solve is 3x minus 4 is bigger than 0.
In fact, does that look like that's the type of equation that you can just solve by directly manipulating the inequality? Right, you can add 4 to both sides. Adding 4 to both sides resolves inequality. You can divide both sides by 3 because that also resolves inequality. So you'll see 3x must be bigger than 4. So x must be bigger than 4 over 3.
Cool. People pretty okay with that? So I guess you could rewrite that domain as 4 thirds to infinity if you like interval notation. Let's try it again. Let's try to find the x-intercept and the domain of log base pi of 4 minus x squared. And maybe in the interest of time, I'll even say, which do you guys want to do first, x-intercept or domain? X-intercept? Domain? Okay, we'll go in order. So let's find the x-intercept. So that means I need to set this equal to 0, solve for x. So I need to solve log base pi of 4 minus x squared equals 0.
Let's go ahead and do it. What do you get when you rewrite that in exponential form?
Yeah. But what is pi to the 0? Doesn't matter that that pi was there. That look like an easy equation to solve now? Yeah, so I guess you would add the x to the other side, subtract the 1 to get 3 equals x squared. So I guess x must be the square root of 3. Unless, is there another number it could be? Negative 3. Negative root 3, yeah. Yeah.
And let's see, just because there are issues with negative numbers inside of logarithms, let's check that both of those are in the domain. Just do a little sanity check.
The positive one is definitely fine. Let's think about what happens when you plug in x equals negative root 3. Let's just double check that. Let's go from the inside out. What's negative root 3 squared is 3. The negative sign goes away. So you'll have 4 minus 3. What's 4 minus 3? What's the log base pi of 1? What's the log base anything of 1? 0. Cool. So it does work. Both of those are solutions. Let's not do domain the whole way out, but what inequality would you need to solve if you wanted to compute the domain? That look like an inequality that you've solved many times in the past? So let's not do it. Instead, let's move on to doing one of the two on this page. Let's find the intercepts, the x-intercept, and the domain of, well, maybe we'll do both. Maybe we'll just do one. Which one would you like to do first, the rational function or the absolute value? Rational function first?
No.
Oh, yeah.
That's a different building.
Rational function.
Rational, okay.
This is the third one.
So, let's find x-intercepts first. What do you need to solve if you want to find x-intercepts?
Second numerator to 0.
Not the numerator. You want to set the whole function equal to 0. So I need to set the ln of x plus 1 over x minus 1 equals 0. So notice that's a little bit different from setting the rational function equal to 0. Cool. So let's walk with that. That's an equation that's in logarithmic form. What do you get when you rewrite it in exponential form? Yeah.
Do we have a sign to show on the bottom? Did we flip them? It's 1 minus x.
I don't know what you're talking about. Cool. What's e to the 0? So I need to solve x plus 1 over 1 plus x divided by 1 minus x is equal to 1. Well, what would you want to do to solve that equation? Okay, let's clear the denominator. So let's multiply the thing on the denominator to the other side. So 1 plus x is equal to 1 minus x. Nice. Go on, let's keep solving. Yeah.
Yeah, so you'll add x over and then subtract it over.
Subtract 1 from both sides, add x to both sides, so you get 2x equals 0, so x is equal to 0?
Yeah.
So it looks like the x-intercept occurs at x equals 0. People okay with that? Let's find the domain. What inequality do you need to solve to compute the domain? Well, what things can you put inside of a log?
Positive.
Positive things. So if you want to find the domain, you need to solve 1 plus x divided by 1 minus x is bigger than 0. And I've got enough time. Let's go through and do it. So what do you need to do when you need to solve an inequality? Solve equality first. So to do that, step 1 is solve 1 plus x divided by 1 minus x is equal to 0. The only way for that to happen is if the numerator is 0, so 1 plus x must be 0, so I guess x is negative 1. Second, find the vertical asymptotes. Where are the vertical asymptotes of this function? So it looks like x equals 1 and x equals -1 are like the interesting numbers. And now we can play the between and beyond game. So let's imagine boss plugging in x equals like 25 trillion. You plug in 25 trillion for x, you'll get 25 trillion on top, -25 trillion on bottom. So it would be negative. Is that bigger than 0? No. So excluding numbers are out. So it must just be the space between. So this is solved by the interval from -1 to +1, including or excluding endpoints. Excluding. I have to exclude 1 because there's a vertical asymptote. I have to exclude -1 because when you plug in -1 you get 0, and 0 is not bigger than 0. So that got kind of fast at the end, but hopefully it's still up. Oh, yeah.